Welcome back to Thermo Shorts. We've been looking or starting to look at open systems. In last class, I talked about these three questions that we want to be able to answer, and we're still focusing on what happens to the mass. We talked about an elapsed time version of conservation of mass, but we also said we won't use this equation very much because when we're talking about open systems, we're generally interested in rate equations. So what's going on at a particular instant in time where we're taking a snapshot of the system to determine the performance. In this case, we know the rate of mass change with time in the system is equal to the sum of all the mass flow rates in minus the sum of all the mass flow rates out. So here we did a couple examples, and the first one's a bit of a silly one using elapsed time. I talked about Mickey and the beanstalk, and I gave some information about Mickey, Donald, and Goofy using water they had in a reservoir to water their beanstalk over time. And if we track all the times that they're taking water out and putting water in, then we can find out how much water we have at the end of the problem. Now, it's important to notice here that we're not talking about mass in this equation, right? This is all liters of water, and liters is a measure of volume. And there's no such thing as conservation of volume. But in this case, because we're talking about liquid water at every case, then we're assuming that the density or the specific volume is approximately constant. And if the density is approximately constant, then what happens is that your volume ends up being conserved. But that's only because mass is conserved. There's no such thing as conservation of volume. Notice we're also neglecting evaporation in this case, which could lead to more water loss. So if I wanted to draw a schematic of this particular problem, I would track my initial volume in this case in my reservoir. I add up all the times we put water in, and I subtract all the times we take water out. And in this case, I think if I did the math right, we end up with 4 liters when we're adding and subtracting. So this is pretty straightforward. But the type of problem we'll do with mass conservation in this class is more like this. So now we have a turbine. The turbine has one inlet port where we have high pressure, high temperature steam coming in, and 2 outlet ports. So in this case, the temperature and the pressure of the working fluid is diminished. So what happens is we're taking some of the energy that's stored in this mass and we're converting it into mechanical energy as the turbine blades spin. We're told some state information at each point, and we're asked to find the velocity of the fluid coming out at 2 and at 3. So how do we do this? First, we're going to assume that the system is at steady state. We know if we're using a rate equation, if we're at steady state, that term, the change in mass with time, goes to 0. So in this case, at steady state, the mass flow rates in, or the sum of the mass flow rates in, is equal to the sum of the mass flow rates out. Remember, last class we talked about how to get a mathematical definition for mass flow rates, and I'm using that here for all 3 of my terms. Notice at the inlet, I was told the volumetric flow rate, which is the area at state 1 multiplied by the average velocity. In this equation, there's a lot of things I don't know, including the velocity at 2 and the velocity of 3. But some of this stuff I can figure out. So I can get the cross-sectional areas at state 2 and state 3 by using the diameter of these ports. And I can get the specific volumes of state 1 and state 2 because they're superheated vapors. And I can also get the specific volume at state 3, which turns out to be a subcooled liquid in this case. So I can look all of these things up using the methods that we've used before. But even after I do all that, and most of my variables I know, I'm still at the point where I have one equation with 2 unknowns, the 2 velocities I'm looking for. So I need another equation. And it's not surprising here that the other equation I have is that the sum of the mass flow rates in is equal to the sum of the mass flow rates out. We're also told that the mass flow rate at state 2 is 20% of the first mass flow rate. So I know that. Then I can use conservation of mass. I know that m dot 1 is my mass flow rate in, and m dot 2 and m dot 3 are my mass flow rates out, but I can express m dot 2 as a function of m dot 1. Then I know that m dot 3 is 80% of the mass flow rate at 1. So that's great. I fixed my states, I know my areas, and I know that the mass flow rate at state 2 is 20% of the first mass flow rate, and the mass flow rate at 3 is 80% of that same mass flow rate. So now, because I'm told the mass flow rate at state 1, or at least I can figure it out because it's A1 V1 over little v1, then I can figure out what the mass flow rates at state 2 and state 3 are. But I don't want the mass flow rates, I want the velocities. So now I have to use my equation for mass flow rate at state 2. I can isolate for the velocity at state 2. I put the known information into my calculator and I check my units. And I get the velocity at state 2 is 17.1 meters per second. I can do the same thing at state 3 and find that the velocity here is 10.7 meters per second. And that's generally how I'm going to do these kinds of rate conservation of mass equations in open systems. Thanks for joining me on Thermal Shorts. I'll see you next time.